This first slide shows a simplified diagram of how most solar grid-tie power systems work. The DC power from the solar array passes through the solar inverter, which converts it to AC power, and then sends it on to the main breaker panel. There, the AC power is either used directly by any loads that are on at the time, or if the solar array is actually producing more power than is being used, the excess power is sold back to the utility company. This turns your kilowatt-hour meter backwards and lowers your monthly bill. The next slide shows what happens to a typical grid-tie solar power system during a utility outage. The red lines indicate electrical power flow, while the black lines indicate no power flow. When utility power goes out for any reason, there won't be any AC power available at your main breaker panel, not even from the solar array and inverter. That's because the solar inverter senses there isn't any AC voltage coming from the main breaker panel, so it shuts down to keep from potentially electrocuting a lineman or a woman who may be working on the lines to repair the cause of the outage. So if you have a grid-tie solar power system like this and there is a utility outage, you'll be without power just like everyone else in the neighborhood. This slide shows the basic components of a grid-tie green hydrogen system. Here we see the same four components from the previous system: the solar array, solar inverter, main AC panel, and kilowatt-hour meter, plus a central inverter, critical load subpanel, electrolyzer, which uses electricity to produce hydrogen from water, hydrogen storage tanks, and a stationary fuel cell, which is like an electrolyzer operating in reverse because it produces electricity and water from hydrogen. Again, the red lines indicate electrical power flow, and the black lines indicate no power flow. The green lines indicate the flow of hydrogen, and the single blue line in the lower right-hand corner indicates water flowing into the electrolyzer. During a utility outage, the main AC breaker panel in a green hydrogen system is dead, just like in the previous system we looked at. However, the central inverter is able to communicate with the solar inverter via the RS-485 cable and keep it running to send power to the critical load subpanel. Loads in this subpanel should be things like your well pump, if you aren't on city water, refrigerator freezer, necessary medical loads, minimal lighting, and the electrolyzer. If these loads are demanding more power than the solar array can handle, or if it's nighttime and the solar array isn't producing any power, the central inverter can draw power from the stationary fuel cell, which produces DC power from the hydrogen gas stored in the on-site tanks. With the electrolyzer being wired to the critical load subpanel, it will be able to produce hydrogen anytime the power coming in from the solar array is greater than the power demanded by all of the loads connected to the subpanel. On the far right side of the slide, you can see a green line going to a fuel cell vehicle. These vehicles should be more readily available by the end of 2015 or early 2016. So not only can a green hydrogen system provide you with clean backup power during a utility outage, it can also produce fuel for your vehicle without you having to worry about what the price is at the pump.